Welcome to the Deep Dive. We take information you're curious about, and, well, we dive deep to pull out the really fascinating stuff.
That's the plan.
And today, you wanted to get a handle on the radial velocity measurements of stars from the Gaia mission, specifically looking at Data Release 3.
Right. Gaia DR3.
So think of this as your way to quickly grasp some pretty amazing cosmic insights without wading through dense papers. Our sources are excerpts all about Gaia's radial velocity results.
Exactly. And radial velocity, it's fundamental here. It's just the speed a star is moving either straight towards us or straight away from us.
Okay.
And we figured that out by looking at how its light is shifted, the Doppler effect, like a siren changing pitch.
Oh.
Same idea, but with starlight.
Right. Okay. So Gaia is measuring this, but on a huge scale. That's the difference.
That's the absolute game changer here. The sheer number of stars and the precision Gaia achieves, it's just unprecedented. We're getting this incredibly detailed map of how stars are moving, which is, well, essential for understanding our whole Milky Way galaxy. Its structure, how it formed, where it's going.
Okay, let's get into that. What was the main driver behind Gaia's radial velocity spectrometer, the RVS?
Well, its primary job, its main purpose, was to nail down the radial velocities for stars brighter than a certain limit. That limit is about magnitude 16 in Gaia's specific RVS filter called GRVS.
GRVS. Okay, so that's like the specific way Gaia measures brightness just for this.
Yeah, it's optimized for the spectrograph.
Yeah.
So job one, measure the speed of millions of stars.
Millions. Simple enough, right?
Well, yes and no, because for the brighter ones among those millions, the RVS does more. It captures detailed spectra.
Ah, okay. Not just the speed.
Right, and those spectra are like treasure chests. They tell us how much interstellar dust is in the way, making the star look redder.
Okay.
They tell us what elements the star is made of, its chemical fingerprint, and even how fast the star itself is spinning.
Wow. So much more than just how fast is it going towards me.
Exactly. It's a pretty complete picture for those brighter stars.
That's amazing. The source material mentions, earlier discussions about the nuts and bolts, the wavelengths, how the spectra are actually gathered. We don't need to get lost in that today, but it sounds complex.
Oh, it is. A whole feat of engineering. But let's jump to the results, specifically Gaia Data Release 3, or DR3. That came out June 2022.
Okay, DR3.
And that release covered the first 34 months of Gaia's operational phase. The mission started collecting science data back in July 2014.
34 months. And the mission might run for 10 years or more.
That's the hope. So DR3 is really just the beginning, relatively speaking.
Right. So what did those first 34 months actually give us in DR3? For radial velocities specifically.
The numbers are just huge. DR3 provided radial velocities for over 33 million sources.
33 million.
Yep, down to about GRVS magnitude 14. And remember, that's alongside the main Gaia mission data, the positions and motions across the sky, the astrometry for 1.8 billion stars.
Billion with a B. It's just mind-boggling scale. So 33 million speeds. And more coming. You mentioned DR4.
That's the next big one, expected around 2025, maybe a bit later.
Okay.
And that one's based on 66 months of data, so double DR3's baseline. The projection is around 100 million radial velocities.
100 million.
And reaching fainter stars, too, down to that GRVS 16 magnitude limit we talked about.
Wow, so almost triple the current sample size.
Yeah.
But getting from raw satellite data to 33 million reliable velocities, the source stressed that the processing is, well, really complicated.
Incredibly complicated, yeah.
Yeah.
The processing pipeline is this huge software system that has to perform incredibly careful calibration.
Calibration for what sort of things?
Oh, all sorts. You've got stray light bouncing around inside the telescope. The instrument itself doesn't spread the light out perfectly evenly. That's the line spread function.
Right.
The detectors, the CCDs, have their own quirks and biases. Cosmic rays hit the detectors and leave little trails.
Like interference.
Exactly. And then there's the challenge of just observing in crowded regions of the sky where the light from different stars overlaps. You have to disentangle all of that.
It sounds like trying to listen to one specific conversation in a really loud, crowded room.
That's a pretty good analogy, actually, yeah. It takes a massive amount of effort to correct for all these effects and make sure the final velocity measurement is accurate.
Okay.
And it's through that whole process that we extract not just the radial velocity, but also that stellar rotation speed and other astrophysical parameters for many stars. But yeah, let's stick with the velocities for now.
Right. So they did all that work, got the 33 million velocities. What did we actually learn from the DR3 radial velocity data? What jumped out?
Well, one of the first things you can do is just map them. See where these 33 million stars are on the sky?
Okay, like a density map.
Exactly. In galactic coordinates, so centered on the Milky Way,
Hmm.
it immediately shows you, where Gaia's RVS has been observing most effectively. The sampling density.
Makes sense. And the source mentioned a histogram, like a bar chart, of the velocities themselves.
Yes, that's super informative. If you just count how many stars have each particular radial velocity, you see this big peak right around 0 km/s.
Which means most stars are moving kind of like us.
Pretty much. That's the bulk of the stars in the Milky Way's disk, orbiting the galactic center more or less alongside the sun. So, relative to us, their radial velocity is low.
Okay, that makes sense. But you mentioned some interesting bumps and a spike in that shot.
Ah, yes. This is where it gets cool. There's a noticeable bump around plus 262 kilometers per second. That velocity clearly flags stars belonging to the Large Magellanic Cloud.
Our neighboring galaxy.
Exactly, moving away from us at that speed. And then there's this really sharp spike way out at plus 494 kilometers per second.
Whoa, that's fast.
Very fast. That's a globular cluster called NGC 32-1. It's known to be a high-velocity cluster, and it just pops right out in the Gaia data.
So the data immediately starts showing these distinct groups, these different systems, just based on their speed.
Precisely. It separates things out dynamically.
What about looking at the median velocity across the sky? Like the average speed in different directions?
Yeah, that map is really revealing too. If you calculate the median radial velocity in different patches of the sky and color code the map based on that, you actually see the rotation of the Milky Way disk itself.
How did that work?
Well, in some directions, you're looking towards stars that are generally moving away from us as they orbit the galaxy, so you get positive median velocities.
Okay.
In other directions, you're looking at stars sort of catching up to us, moving towards us, so you get negative median velocities.
Oh, I see.
And this creates this large-scale pattern across the whole sky. It's literally visualizing the galaxy's spin.
We can see the Milky Way turning.
We can.
Oh.
And what's also powerful about that map is that things moving differently than their surroundings really stand out.
Like local anomalies.
Exactly. The large and small Magellanic Clouds pop out again, clear as day, with their distinct average velocities. You can see the Sagittarius dwarf galaxy stream.
The one being torn apart by the Milky Way.
That's the one. And even individual massive globular clusters like 47 Tucanae and Omega Centauri show up as localized spots with different median velocities compared to the stars around them.
It's like dissecting the galaxy's components based purely on their motion. Amazing. The source also talked about high-velocity stars, stars moving exceptionally fast.
Right. Studying stars with really high velocities, say beyond plus or minus a few hundred kilometers per second, is interesting because they might tell us about, extreme events.
Like what?
Maybe stars ejected from the galactic center, or stars that were originally part of smaller galaxies that merged with the Milky Way long ago, or maybe kicked out of star clusters.
So they're like outliers that hint at past drama.
Kind of, yeah. And the document showed how important data quality is here. If you just plot all the measured velocities, you see these long wings extending to very high positive and negative values.
But maybe not all real.
Probably not. A lot of that is likely spurious measurements, just errors. But if you filtered the data, keeping only measurements with a high signal-to-noise ratio...
The cleaner data.
Exactly. Those wings mostly disappear. But the real high-velocity populations, like the stars in the Large Magellanic Cloud or that speedy cluster NGC 32-1, they stand out even more clearly.
So filtering is key to separating the signal from the noise, especially for these extreme cases.
Absolutely crucial. Data validation is a huge part of using Gaia data effectively.
Now, to really drive home the power of this, the source zoomed in on one specific object,
Yeah.
the globular cluster 47 Tucana.
Why 47 Tuc?
47 Tuc is just a perfect test case. It's this big, bright, relatively nearby globular cluster, just packed with stars.
Okay.
And the DR3 data for it is fantastic. There was this diagram showing the star's brightness versus color magnitude diagram. All the stars Gaia saw in that direction were plotted.
Right.
And the ones where Gaia actually measured a radial velocity were colored based on how uncertain that velocity measurement was. Showing the precision.
Yeah, and it showed, as you'd expect, that for the brighter stars, the uncertainties get smaller. We get more precise speeds for brighter targets.
Makes sense. And there was a sky map, too.
Yes, showing the stars in 47 Tuc on the sky, colored by their brightness. And the really remarkable thing is that Gaia's RVS got velocity measurements even right into the super dense core of the cluster.
Where the stars are all jammed together.
Incredibly close. And it measured velocities for stars all across the different evolutionary stages you see in a cluster like that. Red giants, stars on the horizontal branch, asymptotic giant branch stars.
So a kinematic snapshot of the whole cluster population.
Pretty much. You can study the internal motions, how different types of stars are moving within the cluster's gravitational pull.
And the precision you mentioned, how good did it get for 47 Tecket?
It's really impressive. The formal uncertainties, the error bars on the velocities, they range from maybe a few kilometers per second for fainter stars down to just a few hundred meters per second for the brightest giants at the tip of the red giant branch.
Meters per second, not kilometers.
Meters per second. That kind of precision is just phenomenal. It lets astronomers probe really subtle effects within the cluster, like how it rotates internally, or maybe even search for evidence of things like intermediate mass black holes.
That's an incredible level of detail. Just amazing. Okay, so finally, looking ahead, DR4 is coming with maybe 100 million velocities. And the source mentioned using deep learning. How does that fit in?
Right. AI and machine learning are becoming really important tools here. Deep learning algorithms are basically being trained on the vast amounts of Gaia data
To do what?
to get even better at recognizing patterns. They can help automatically identify potentially spurious velocity measurements, flag data affected by contamination from nearby stars, and generally improve the quality control.
So making the next data release even cleaner and more complete.
That's the goal. Minimize the bad data, maximize the good science. These algorithms can potentially sift through the data in ways that are faster and maybe even more sensitive than traditional methods for some tasks.
Okay, so better tools for an even bigger data set. Sounds promising.
Definitely.
So let's sort of wrap this up. This deep dive into Gaia DR3, it really underscores what a monumental data set we're dealing with.
Absolutely. DR3 was a huge step forward, giving us this massive, precise catalog of stellar speeds. It's providing truly unprecedented views of how our galaxy works.
Yeah, the sheer numbers, 33 million velocities already, 100 million on the horizon, and that incredible precision down to meters per second in some cases. It's just stunning.
And we're already seeing the payoff, visualizing the Milky Way's rotation, picking out the Magellanic Clouds and streams, finding high-velocity stars, dissecting clusters like 47 Tukh.
It really feels like we've opened a new window onto the dynamics of the cosmos,
It definitely does.
which leaves you wondering, with DR4 and then the final Gaia release still to come, what other structures, what other motions are hiding in that data? How will knowing exactly how billions of stars are moving help us finally piece together the complete history and maybe even the future of our corner of the universe? Something amazing to think about.